Okay, so now that we're well acquainted with matrices and we know all kinds of notions and terminology associated to matrices, the next step is to understand operations on matrices, how we add matrices and how we subtract and how we multiply and so on. And only after we do that, that's going to be the topic of this lesson. After we do that, we will be able to start seeing the vast applications of matrices. Why are they good? What are they good for? And it's going to be all over this course and far beyond. So what we're going to see is expressing what are called linear operators with matrices and expressing systems of equations with matrices and so on. So the first thing we need to define, and we've done it several times already in this course when we defined new things, is what is equation? Okay, so equation, equality, I would say, equality. So A equals B, two matrices are equal if they have exactly the same size. Okay, so if A is m by n, then B has to be m by n, and entries. So all the entries have to be the same, and their sizes have to agree. So for example, so I'm not going to write two matrices that are equal, because that would be writing the same matrix two times. But for example, 1, 2, 3, 4 is not the same as 1, 2, 4, 3. They have the same size, they have the same entries, but in different locations. They're different. So maybe I should emphasize exactly the same size and exactly, I would add a few words, and exactly the same entries in exactly the same places. Okay, so this is not equal. And likewise, if you look at this matrix, 1, 2, 3, 4, it's not the same as 1, 2, 0, 3, 4, 0. In some sense, they carry exactly the same information. So a zero entry is kind of informationless in some sense, but they're not the same. This one is a 2 by 3 matrix, where this one is a 2 by 2 matrix. Okay, so is this clear? Okay, so that's equality. Now how do we add matrices? So addition and subtraction, they can be both defined simultaneously, subtraction. So this is just done element-wise. Element-wise. What do I mean by that? I mean that you take the element in the position 2, 3 and add it or subtract it to the element in the position 2, 3. Okay, so here's an example. So suppose we have the matrix 1, 2, 3, 4, 5, 6. And we want to subtract the matrix 0, 1, 2, minus 3, 4, 6. Okay, we do it element-wise. 1 minus 0 is 1. 2 minus 1 is 1. 3 minus 2 is 1. 4 minus 3 is 7. 5 minus 4 is 1, and 6 minus 6 is 0. So this is how we do matrix addition or subtraction. Is that clear? Okay? Everybody good? Very straightforward. Okay. The next notion is not yet multiplication, but multiplication, or let's call it scalar. A scalar is just another name for a number. A number is called a scalar, okay? Scalar times a matrix, or scalar multiplication of matrices. Scalar times a matrix. Again, element-wise or entry-wise. So what do I mean? What do I mean? Example. And when the example is completely obvious and I see that you understand, I'm not going to try to say it in a million words. It would just get confusing. Does everybody understand how to add and subtract matrices? By the way, this can only be done when they have the same size. Okay? Element-wise, for matrices of same size. You can't add or subtract matrices of different sizes because it's not going to work element-wise. You wouldn't know what to do. Okay, so here's an example. Suppose I want to do 3 times the matrix 1, 2, -1, 0. What is 3 times this matrix? It's just 3 times every entry. So it's going to be 3, 6, -3, 0. I multiplied each entry by the number, by the scalar. Is this clear? Okay? And you can multiply a matrix of any size by a scalar. You just multiply each entry. Okay, good? Everybody? Okay. Properties. A big, long list of properties of addition and scalar multiplication. Properties. So property number 1, maybe I'll list them over here. So property number 1, addition of matrices is commutative. A plus B equals B plus A. I'm not going to write formal proofs for all of these. I'll do 1 or 2 so you see the idea of how we prove this stuff abstractly. But as we list them, there are going to be, I don't know, 10 or 11, and there are going to be more for multiplication later. Just see that you believe them, that they make sense, that they're convincing. So since the addition is entry-wise, it doesn't matter if we add the 3 and the 5, or we reverse and add the 5 and the 3. Okay, does everybody see that this is probably true? That's not a formal proof. Taking an example is never a formal proof. We'll see an example of a formal proof in a minute. Okay, addition of matrices is associative. A plus B plus C equals A plus B plus C, whether you first add A and B and then add C, or you first add B and C and then add it to A. Okay, so that's associativity of matrix addition. A plus 0 equals A. What is 0 here? Right, 0 is the 0 matrix, the matrix in which all the entries are 0. So if you take A, any matrix, add the 0 matrix, meaning you're adding 0 to all the elements, you'll just get A back, right? So 0 is in fact the additive identity for addition of matrices. Okay, and we should emphasize that for all these properties hold when A and B and C and 0 all have the same size. So you can carry out that addition. Okay, so this is kind of implicit in listing these properties that we're working with matrices that you can actually add. Okay, property number 4. Remember we had the notion of a minus A. So if we take the minus A matrix, meaning we just put a minus sign on all the elements, and we add it to A, what would we get? Right, we'd get the 0 matrix. Okay, so the matrix which we denoted by minus A, which was just sticking a minus sign on every entry, is in fact the additive inverse of the matrix A. Okay, good. And here are some properties for scalar multiplication. So scalars I'm going to denote by alphas and betas. If you take alpha times A plus B, you get alpha A plus alpha B. So this is kind of a form of a distributivity law between addition of matrices. Note that this plus is a brand new plus. It's not the plus of numbers. It's plus of matrices. And this equal sign is a new equal sign. It's a quality of matrices. And this 0 is a new 0. It's the 0 matrix. Okay? So just looking at this, if this were the first thing you'd see, you wouldn't know that we're even talking about anything other than numbers. But we're talking about matrices and these new operations, and everything requires verification and proof. Okay? Okay. And I'm emphasizing this because not everything you know for numbers extends automatically to new things. In particular, in a few minutes, we're going to define multiplication of matrices, A times B, and we're going to see that it breaks all your intuitions. Many things that you know for multiplication of numbers are no longer going to hold. Okay? Okay, so addition and scalar multiplication still behave well with respect to all these axioms that we're used to, like commutativity and associativity and distributivity and additive identity and additive inverse and so on. Okay, alpha plus beta times A is the same as alpha A plus beta A. So this distributivity holds also if we first add and then multiply. Okay. 7. Alpha times beta times A. So this is just a product of two numbers. Alpha and beta are scalars. So alpha times beta is just a number. When you multiply it by the matrix A, it's the same as taking alpha times beta A. You first multiply the matrix by the scalar and then by the other scalar. Okay, you should be convinced that these are the same. More properties. 8. Remember, we had the notion of a transpose, where you replace the rows of the columns in the rows. Okay, so if you take two matrices, add them, and then transpose the sum, it equals the sum of the transpose matrices. This requires thinking. Why is this true? It's not hard. Well, I'll in fact prove this one formally, okay, because it's less intuitive maybe than these, but it's once it's written as a property and proved, you can use it. 9, A minus B transpose is the same as A transpose minus B transpose. 10, alpha A transpose is the same as alpha times A transpose. And finally, A transpose is the same as A. Okay? This in fact is a property that's not related to addition or scalar multiplication. It's purely a property of the transpose operation, but nevertheless I added it in this list. Okay, so let's see how we prove at least one of these. Let's do, for example, number 8. Okay, how do we show that if you take two matrices, A and B, add them using matrix addition, and then take the transpose of the sum, you get the sum of the transposes. Okay, so let's prove that. So proof of 8. So what do we need to show? There's a claim there that two matrices are the same, that A plus B transpose is the same as A transpose plus B transpose. In order to show that they're the same, we have to show two things: that they have precisely the same size and that they have precisely the same entries. That's what it means for two matrices to be the same. So let's do that. So let's first make a size chart. So sizes. So the size of A, let's make a little chart like this. So there's going to be a matrix and a size. So A has some size, let's say m by n. What is the size of B? Right, it has to be the same because we're adding them. So B does not have a choice, it's also m by n. What is the size of A plus B? When we're adding two matrices, we're doing it entry-wise, doesn't change the size. It's still going to be m by n. Do you agree? Okay. What is the size of A plus B transpose? If A plus B was a m by n matrix, its transpose is going to be, very good, n by m, right? Because the number of rows now becomes the number of columns, and vice versa. Okay. What is the size of A transpose? A was m by n. A transpose is n by m. B transpose is also n by m. And therefore their sum, A transpose plus B transpose, is also n by m. Okay? So the point is that the left-hand side, A plus B transpose, has size m by n. This is the matrix sitting in the left-hand side of what we're trying to prove. And the matrix sitting in the right-hand side, A transpose plus B transpose, has the same size. So both sides of the equality that we're trying to prove have the same size. That's one part of it. Now we have to prove that they have the same entries. So entries. Is it clear what just happened? Okay? It may look like a lot of writing down for saying almost nothing. That's true. That's in fact true because this is very easy. Okay? When we'll prove more sophisticated things, then these numbers would, and maybe there would be more matrices involved, and even carrying out this part of the proof might become a bit more, a bit less straightforward. Would require thinking and some arguments and so on to get to equality of sizes even on both sides. What about entries? So we want to take the ijth entry of this matrix and show that it's precisely the ijth entry of this matrix. Let's do that. So A plus B transpose the ijth entry. For I and j, abstract. I don't know what I and j are. Any I and j. Okay, what is it? So the ijth entry of a transpose is the jith entry of the original. So this equals A plus B, the original matrix, ji. That's how the transpose is defined. The ijth entry of the transpose is the jith entry of the original. Do you agree? Okay? And you can see the notation playing a role of saying a lot of stuff and just writing it down and making it very precise without writing down a lot of words. Okay. Now, let's temporarily denote the elements of capital A by little a's and the elements of capital B by little b's. So the jith element of the sum is the jith element of the first matrix. Or we don't even need the little. I'm sorry, let's not do that. So it's the jith element of A plus the jith element of A plus the jith element of B. That's the jith element of the sum because addition of matrices is defined element-wise. Okay? Now, what is the jith element of A? It's precisely the ijth element of A transpose. And the jith element of B is the ijth element of B transpose. That's how the transpose is defined. And the ijth element of A transpose plus the ijth element of B transpose, by definition of addition, is the ijth element of their sum. Okay? So the ijth element of A transpose plus B transpose is the ijth element of A plus B transpose. So the entries agree as well. Okay? So these two parts of the proof taken together prove that in fact this and this are the same matrix. They're equal. They have the same size and precisely the same entries. Okay? It may look very tedious. It may look very tedious, but this is the way to prove things formally. And it's not hard. It's just kind of confusing the first time you see it. You have 10 more of these to practice on. Okay? Try to write them down. Try to spell them out very carefully using this approach, this way of expressing yourself. Okay? They're all at the same level of difficulty. You just have to write them down very carefully. Okay, good, everybody? Okay. Good. Okay. I think we're ready to start multiplication of matrices. That's a bit more, less naive, okay? It's kind of surprising the first time you'll see it. Let's do it in a separate clip.